In this video, we're going to look at what happens to acids when we put them into water. Unlike NaCl, acids are covalent compounds because unlike ionic compounds that transfer electrons from one element to another, the electrons that form covalent bonds are shared between the two atoms that are bonded. This means that acids are going to react very differently than ionic compounds, even if the basis for those interactions is the same. What exactly does that mean? Well, we know by now that water is a polar molecule. Its oxygen has a partial negative charge, and its hydrogen has a partial positive charge. This must also be true on the acid structure that we see here. So this acid is CH3COOH. This is the structure of acetic acid. And if we look at the oxygen and hydrogen here, we know that oxygen, just like on water, has two lone pairs that I've added here. And we know that oxygen has a much higher electronegativity than hydrogen, meaning that it is going to pull the electrons in its bond closer to it, giving the oxygen a partial negative charge and the hydrogen a partial positive charge, which means that the partial negative charge on water can attract to the hydrogen on the acid like this. However, that's not where the interaction ends. So water can actually use its dipole in order to change the structure of this acid, and we can see how by looking at water's lone pairs. So we know that lone pairs are made of electrons, and we know that electrons don't like staying close together because anything with the same charges want to repel, which means that these lone pairs will constantly be looking for a way to move as far away from each other as possible. Well, what this means is that we can take one of the lone pairs and move it away from the other lone pair towards the strongest positive charge we can find on the hydrogen on the acids. Now, what this means is that this lone pair is going to move away from the oxygen where it exists as a lone pair and actually turn into a bond with the hydrogen here. Well, how is that possible? Because hydrogen can only make one bond. Well, if we're going to be making a new bond with this hydrogen here, the old bond here between the hydrogen and oxygen on the acid needs to break. Now, we can't just create or destroy electrons, so we can't make these electrons disappear, but if we break this bond, this oxygen will be missing electrons. So instead, we can take the two electrons from the bond and move them to this oxygen here so that they become a lone pair. Now, what this effectively means is we've taken one lone pair from water and turned it into a bond, and broken a bond on the acid and turned it into a lone pair, as we've seen here. The result is that this hydrogen has been broken off from the acid here and added to water. So we can see that water is able to use its dipole in order to remove a hydrogen from acids such as acetic acid here. Now, if we look at the products over here that we've gotten, we now have an oxygen with three lone pairs, and this lone pair here came from the bond that used to be between hydrogen and oxygen on the acid. Now, if we look at the direction where the electrons move, the electrons are moving from the bond to oxygen, which means that the oxygen in this acid has gained electrons, which means if anything has gained an electron, that means that this oxygen is now going to have a full negative charge. Now, this is different than before, where the oxygen used to have a partial positive charge because of unequal electron sharing, but because we broke this bond and moved the electrons to the oxygen like this, that means that this oxygen has actually gained a full negative charge from taking electrons that it did not used to have before. Well, if we've made a negative charge, that must mean that we made a positive charge somewhere else, and we can see that by looking at water. So if we look at the lone pair here that moves to the hydrogen in order to make a new bond, so again, if we think of this lone pair as being this bond, we know that this bond used to be a lone pair. So what this means is that this lone pair moved away from oxygen and to the hydrogen, which means that this oxygen has lost electrons because they moved away from it, which means that this oxygen has fewer electrons than it used to. And anything that loses electrons is now going to have a full positive charge, and that is exactly what we see. This is very interesting because, again, our starting compounds are both covalent. Neither of these compounds have an ion within their structure. But because water used its dipole to pull the hydrogen off and break a bond, that results in one half of this molecule gaining electrons and one half losing electrons, which is fundamentally different than dissociation reactions, because in dissociation reactions, the two halves that are separated by water were already charged before. If we take a look at the overall reaction here, we can write out a general reaction for this type of interaction between acids and water, where we start with an acid reacting with water. The water again pulls this hydrogen off so that we get CH3COO, missing the H of course, but in place of the hydrogen we have a negative charge. Conversely, this hydrogen has been taken by water, which means that we have this weird H3O molecule here, and because it lost a lone pair in order to make the bond, it now has a positive charge. Now again, because acids are all covalent compounds but produce ions when we put them into water, that is why this type of reaction is what we call an ionization reaction, because we are producing two ions when neither compound had any ionic charge before. In the next video, we're going to take a look at what happens in the opposite of acids, bases, when they undergo ionization reactions in water.